Good morning. Thursday, January 14th. So I'm not sure how many of you heard, but last night they had a meeting, and on Saturday they're going to do an emergency board meeting to discuss the reopening of MSDWT. A few other schools that kind of mirror our district in the past, like when we have snow days, they have snow days, stuff like that, have postponed their reopenings until into February. I don't know why, if everything was going to plan, I'm not sure why you might have a Saturday morning board meeting, but needless to say, I spent some time getting the room back set up for that and getting the seating charts made. But it looks like they're rethinking whether or not we'll have students next week. So just keep that in mind. That is interesting news in our community for right now, I guess. So there we go. Is there anything else on this that I should talk about? Nope. That's it. All right. Back to the discussion of thermochemistry. So if we take a look yesterday, we showed you by adding two different things together. Something that is warmer is going to give energy to something that is of lower temperature. Something that has higher temperature, it's going to give something energy to something with lower temperature. Just like pressure goes from high areas of pressure to low areas of pressure, high temperature heat travels from high temperature objects to lower temperature objects. So we took metal versus water and tried to make the masses of those two equal by putting the same difference in temperature that we did of equal masses of water. Well, the equal masses of water showed that they met somewhere very close to the middle. When we put the metal that was much hotter, or 100 degrees, versus the water that was 0 degrees, we found that it didn't meet anywhere close to the middle. It was actually quite closer to the 0 degrees Celsius for the water. Then when we did water and ice, we noticed that it met further from the middle than when we did just water and water. And the takeaways for that is obviously that there is some energy needed for the water and ice. That's a terrible E. There is some energy needed to break basically that crystalline structure. And with the metal and water, there must be some differences in the heat capacities of these two things. We have to infer that since water basically got itself right about in the middle, and the metal, when it was put in the water, or the water was poured over the metal, it did not get as far away from the temperature of the starting water at 0 degrees. So water has a higher heat capacity. Meaning that it would take more energy to change the temperature of that water. 1 degrees, 1 gram of that water, 1 degree Celsius, versus the metal itself. And you probably experienced this in your life or whatnot. You're sitting there staring with the metal spoon, and you walk away for a second. You come back, you try to grab the metal spoon. It's heated up extremely quickly. Or if you've ever like cooked a piece of pizza or something in an oven, or everybody has these air fryers now. If you take and put that on like some aluminum foil, you know, you usually, if it's just a thin sheet of aluminum foil, you don't really need like a hot pad or a mitten like you would if you had a pan or something that was more massive, because the aluminum foil is able to, you know, it's not very massive, one, and two, it has a pretty low heat capacity. So it's something like you can put in there with your hands, and then even though it's been cooking for you know, 10 minutes at 400 degrees or something like that, you know, you open it up, let a little bit of the heat out, reach in there, and usually you can grab that just with your fingers. Not that you should try this experiment at home, but yeah. So let's take a look here at these practice problems. Did anybody try these and not get the answers to the sides? Let's do one just to make sure that we get it. Let's do this one. Calculate the amount of heat in kilojoules needed to raise the temperature of 60 grams of water from 35 degrees Celsius to 100 degrees Celsius. So right there, I believe we get a change of 65 degrees Celsius. Here we have the mass. So here is our delta T, and here is our M. We know that Q equals ms delta T. Our S for water is 4.184 joules per grams degrees Celsius. Our change in temperature, 65 degrees Celsius. I'm going to go ahead and cheat and put a little dot there. So at least my answer has two significant digits. And if we take a look here, we have 60 grams. So 60 times 4.184 times 65.
It's 16,317.6.
So we're going to round that to two significant digits. That's going to give us 16,000. But then I'm going to change that for every, since this is joules, for every 1,000 joules, we get 1 kilojoule. Move the decimal place over, we get 16 kilojoules. Looks like they went 3 significant digits because they assumed that these were perfect numbers or something, but cool. Now, the question that put us near the end yesterday was, can you just make the change in temperature always be positive? And that becomes a problem whenever you're setting things like this up. So we have a 100 gram block of zinc at 90.5 degrees Celsius is brought into contact with a 100 gram block of aluminum at 17.2 degrees Celsius. If all the heat is conserved when the system reaches thermal equilibrium, what will the temperature be if the heat capacity of zinc is this and the heat capacity of the aluminum is this? Well, basically what we want to do is we want to have our delta H absorbed and then delta H released, but we need that negative sign there. It's basically that amount of heat of one has to equal the negative amount of heat of the other one. So let's take a look. This was at 95 degrees. I'm sorry, 90.5 degrees Celsius. And then the aluminum was at 17.2 degrees Celsius. So if we, and one way you can do this is you can set up one problem and then set up the other one. But the problem here is that we're trying to find the final temperature. So that is going to be in both of them. So if we do this, ms delta T equals negative ms delta T, we should be good, because the temperature of one is going up and the temperature of the other one is going down. So if we put that negative there, that will equal each other out. So let's take a look. 100.0 grams for the zinc. Specific heat capacity for the zinc is 0.38 joules per grams degrees Celsius. The delta T, well, if we recall, delta T equals the final temperature minus the initial temperature. Switch those. T of F minus T of I. So we don't know the final temperature here. So T of F minus 90.5 degrees Celsius. So that's the setup for our zinc side. And if you wanted to, you could go ahead and multiply all that through and then set up the other side. But I'm going to go ahead and take that and put it equal to, we have a 100-gram block of aluminum. And it has a specific T capacity of 0.9. And we have an initial temperature of 17.2. So we want the temperature final minus 17.2 degrees Celsius. Now what we can see here is the fact that, running out of room, the fact that we know this is going to be a smaller number minus this, that's going to make this whole thing a negative number. And that's why we have that negative there. And you could put the negative over here. It doesn't really matter because basically we're setting these equal to each other. And the amount of heat that this one has lost has to be equal to the amount of heat that this one has gained. So I'll make sure all my numbers are correct here. All right. So 100 times 0.38 gives us 38. So that's going to be 38. And then we're going to multiply that by T of F minus 3,439. If we take a look here, I think we're going to end up with the grams and the joules. I'm going to keep degrees Celsius somehow. So I think it's going to be stuck here, and we're going to end up canceling it out here. But we'll go ahead and continue with this part. We know it's going to be degrees Celsius in the end. So if we take negative, so we're going to get 90 T of F minus 1548. And we're going to have the negative sign on that. So we can have that be negative, and then we can change this to plus 1548. So now if we take a look, we need to get the T of F on one side, and basically we're solving for T of F. So if we add 90 to this side, we get, not a terrible room, 128 T of F equals, we'll add 3439 to this side. $49.87. And then basically we need to just take that divided by the 128. So basically set up two equations using the MS delta T, and then solve for T of F. Now the question posed yesterday was how important is this negative sign? If we weren't solving for the final temperature, I think you can get away with just figuring out, okay, how much energy do we have here? and then just translating it into the energy lost by the other one, because you do know that one has to be lost and one has to be gained. But whenever you're doing searching for the final temperature, if you don't put that negative sign on there and keep these separate, it's going to be, you're not going to be able to get the right answer on that. So it's kind of a situational thing. But if you do this always, then it's never a problem. But I think maybe last semester, we would sit here like a problem like this. We might solve this first and then just plug that heat into this, and we would be able to get that with no problem if we looked at the temperature change as absolute. With this, it doesn't work so nicely. Questions there? Yeah, I get it. Make sure I'm getting the right stuff done for today. Heat of vaporization. All right, cool. Discuss multiple step problems and heat transfers. Okay. Heat of fusion, heat of vaporization. All right, so you can try these problems. If you are only going to try one, you should have tried the one we did, but it looks like number 8 has you calculating the final temperature again. So that's probably going to be one of the more difficult ones, because as I said, if you're just finding one of the other variables, you can solve one side of the entire equation. That is the, unless they had you solving for the initial temperatures for each thing would be different. So but that is the only thing that is the same on both sides of the equation. So if you are solving for that final temperature, you do have to do it the long way. All right. So again, going with what we did yesterday, putting the ice in there as the last little part of the demo. That gets us to heat association with phase changes. So you should know this, that solid has the least kinetic energy, liquid right up there, a little more, and then what are they doing here? Oh, I'm sorry. Let me write that up here. Solid to liquid to gas. So if we take a look, solid here, lowest amount of kinetic energy, and gas, highest amount of kinetic energy for the states of matter that we look at. If you're going from solid to liquid, we call that melting or fusion. And if you're going from liquid to solid, we call that freezing. Liquid to gas, vaporization. There are 2 types of vaporization. Evaporation, which occurs on the surface of the liquid, and boiling, which occurs beneath the liquid surface. And gas to liquid, we have that as condensation. Does anybody know the term for solid directly to gas? I'll open up the chat for you if you just want to type today.
Sublimation, right?
Sublimation. How about the opposite, gas to solid?
Deposition.
Good. Sublimation. A lot of people know the sublimation. Deposition, not so common, because I think we've probably all seen, like, if we're in theater or whatever, we've seen dry ice put in to water or whatnot to give that a fog, but we don't often get to see the deposition. This would be basically the depositing of the gas into a solid form on something. For any of these, what we call phase changes, the temperature remains constant. That's coming up. Heat energy is required to go from solid to liquid. So we would call this process an endothermic process. melt ice and turn into water, endothermic. If we're looking at the ice as a system or the solid as a system, that would be endothermic. It's gaining energy. The value for that per gram is 333 joules. Keep in mind that even though it takes the same type of thing, Q equals MC delta T, or MS delta T, since there is no change in temperature here, you would not have the delta T. So you take the mass basically times, and this is actually called heat of fusion, not like the specific heat capacity of it, but it's the same type of formula. The mass times the delta H of fusion. So that's 333 joules per gram. You could also have this as the molar heat of fusion. It would just, instead of being joules per gram, it would be joules per mole. Heat of vaporization, it's the heat required to do the same process, but in a sense, heat a liquid up to the point where it turns into a gas. Water obviously has a boiling point of 100 degrees Celsius, and this is a little bit higher. This is 2260 joules per gram, and you might call that the delta H of vaporization. Again, this one is in grams, but there is also a molar heat of vaporization. Boom. And since we are going on here, if we go this way on this diagram, then we are gaining energy for the system. If we go this way, we are losing energy for the system. But it is sometimes hard for some people to think, like, if we want to freeze something, we have to take energy away from it. A lot of times we get stuck in our mind that we give something coldness, or it feels cold, so we think that, you know, it's endothermic or whatnot. But if we're freezing something, that is exothermic to that, whatever we're freezing. We've got to take energy away from it. If we're melting something, that's when we're putting energy into it. If something is evaporating, that means the particles that were liquid, they are gaining enough energy to go to vapor. And that is endothermic. And condensing, obviously the opposite, exothermic. And anytime you do these, there is no change in temperature. So if we want to take 250 grams of water and change it to ice, if we had the molar heat of fusion, we would need to change this grams to moles. But since up here we have the mass conversion, we can just do it simply. 250.0 grams of H2O liquid. And we are going to, for every 1 gram, require the removal of 333 joules. So if we were to calculate the amount of energy associated with changing this, times 333, we would get, say it doesn't give us a unit, so that's going to be 83,250 joules, which we can then convert to 83, and well, it doesn't matter, 83.3, actually 83.25, we have 4 significant digits here, 83.25 kilojoules. If we were to do it with the heat of vaporization, instead of using the 333 joules per gram, we would use 2260 joules per gram. Keep in mind, since we're calculating the amount of energy associated with changing this, a lot of times you'll see a question that sits there and says, well, how much energy is released? This is the amount of energy released. If we were talking about the change of energy and they wanted us to talk about, you know, and they just weren't saying that it is exothermic or whatever, we may need to put the negative in front of there. Now, these problems are the longer ones. So if we have an example here, we have the changing of one state of matter and then the changing of another one. And I suggest you make either something like this or put little changes like solid to liquid and then have the math for that. And then a change in temperature, because right here, we can see that if this is temperature, and this is kinetic energy, we can see here, we bottom out or we flatten out with the temperature. There is no change, but here, once we get that phase change done, we do have another change in that temperature. So basically, if you're going from solid to liquid, you've got to get the energy required to change it from solid to liquid first. And then if you're going any change in temperature, you need to add that change in temperature in there. So 72.3 grams of ice at negative 15 degrees Celsius. So we're starting down here at negative 15. Has heat added to it until it becomes steam at 145. So what you can see here is we have one problem here, a change in temperature up to 100 here, changing that then into steam at 100 degrees, and then changing that up to 145 degrees. Questions about that? All right. So let's first off get it from negative 15 degrees up to 0 degrees. So if we take a look, Q equals ms delta T. The delta T is going to be 15 degrees Celsius. The S for ice. So the specific heat capacity for ice is different than water. It's 2.1 joules per grams degrees Celsius. That's the thing. Every substance, even if it's in different states, is going to have a different specific heat capacity. So you need to be given that, or you need to use a reference guide to obtain it. And the mass of this water is the mass of this ice is 72.3 grams. Grams will cancel out, degrees Celsius cancels out. We end up with a certain amount of joules. 72.3 times 2.1 times 15.
The answer is 2,277.45.
If we were keeping tabs, this is actually 15.0. The 2.1, we're assuming that that is a perfect number. So we'd have 3 significant digits there if we were keeping tabs on that. And this is in joules. That's something we also want to keep in tabs because sometimes you'll be given the heat of vaporization in kilojoules per gram. But this is in joules. So now we had to calculate the energy required to melt. Very nice because we have this in grams and not in moles. So we don't have to do any conversions here. 72.3 grams, except for every 1 gram is the heat of fusion, 333 joules to melt. $72.3 times 333.
It's 24,075.9.
So if we take a look there, we have 24,075.9 joules, a much larger amount of energy to melt this than it is to go from negative 15 to 0. Calculate the energy required to heat the water to boiling. So again, we have a change in temperature. So ms delta T from 0 to boiling for water is 100 degrees Celsius. Specific heat capacity of water is 4.184 joules per grams degrees Celsius. And the mass for this is 72.3. So 72.3 times 4.184 times 100
It's 30,250.32.
30,250.32. Calculate the energy required to vaporize the water. So if we calculate the energy required to vaporize the water, that is at 100 degrees. This is our fourth step. So for that, we are going to need the delta H of vaporization, which is 2260. Again, we have 72.3 grams, assuming we've not lost matter, which we shouldn't have. Every 1 gram is 2260 joules. 72.3 times 2260.
It's 163,398.
So if we take a look there, 163,398 joules. Calculate the energy required to heat the steam from 100 to 145, our last and final step. We have an ms delta T again. So the change in temperature is going to be 45 degrees Celsius. The specific heat capacity for steam is 1.7 joules per grams degrees Celsius. And our mass for this is still 72.3 grams. Again, we have the cancellation of everything except for joules. 72.3 times 1.7 times 45.
The answer is 5,530.95.
So now we want to add all of these up. I don't think I can say all of that in the amount of time that she requires. So 2277.45 plus 075.9 plus 30,250.32 plus 163,398 plus 5530.95. And we get this big old number. If we change this to kilojoules, actually before we change it to kilojoules, since we added these up in joules, the least specific is the 1,000th place. So that means if we have 225532, we need to round that using our addition subtraction rules right there. So it'd be 226. And then if we were to change this from joules to kilojoules, we would simply divide by 1,000. Questions on any part of that? It is a long process, but basically you just break it down into each thing that's going on. Again, that's the cool thing about energy is it's a function of state. All you care about is the where it is when you're looking at it. Makes sense. So we're looking at it between here and here, here and here, here and here and here and here, all those different places. Is that all I wanted to get done today? In infusion, show connections with formula for heat capacity. Yep. So basically, again, that heat of fusion stuff. Again, keeping in mind ms delta T. Since you don't have a change in temperature, that's taken out, and it's instead of it being your specific heat capacity being joules per grams degrees Celsius. If you take out the temperature, it's just joules per gram. So I mean, that's the connection with the formula. I would suggest you do a few of these over the night. 13, 14, and 15 are basically practice problems that would take you through everything we've covered so far. And what is tomorrow? Oh, tomorrow it looks like we're doing a few of those problems as well. And there is no test Monday. Don't forget, We'll do a few review problems tomorrow, set you off nice for the weekend, and then come back on Tuesday with enthalpies of formation, which basically, again, we're going to look at elements and see how they come together to form compounds and that type of thing, and the energy of the reactions. Questions? If you do, we've got 12 more minutes. Otherwise, I suggest you go do maybe, you should probably be able to do at least 2 of those problems within 12 minutes. Well, have a good day. Hopefully we didn't break any hearts if we do end up not coming in next week.
Thank you, Mr. Jackson. Have a good day.
Hey, you too.
Mr. Jackson,
Yeah, what up, Sam?
I'm not going to be here tomorrow, be in class tomorrow, because I have a doctor's appointment for most of the day. So I just wanted to let you know.
No worries about that at all. So if you look at the pages that I said, 13 and 14, they do actually have the answers there.
Okay.
So I would just pick a few problems on the Zoom. I'll probably do a couple problems as well. And that's it. I mean, it's basically reviewing what we've done up to this point for the week.
Okay.
Yeah.
Okay.
Cool.
See you on Tuesday.
See you Tuesday, Sam. Have a great weekend. Dylan, you good? I'm going to go ahead and end this so that I can post it
All right.
unless you have questions. You okay? Okay.